Hey everyone, thank you for joining us today for our quantum speaker webinar series hosted by ATARC's Global Quantum Working Group. I'm Jason Lee. I'm one of the group's government co-chairs. We are excited to welcome Chander Velu to speak with us today. Chander is a professor of innovation and economics at the University of Cambridge. He heads the Business Model Innovation Research Group at the Institute for Manufacturing. This talk explores the potential impact of quantum computing in transforming the ways firms create and capture value in order to increase productivity and economic growth. If you have any questions, please feel free to use the Q&A feature. We will save Q&A for the end. Hopefully we'll have time to answer a lot of questions. But please, Chander, take it away.
Thank you. Thank you very much, Jason, and thank you, Amy, as well, and appreciate the opportunity to present today. Delighted to be here. So the topic of my talk is quantum computing and economic productivity, the role of business model innovation. So the outline of my talk is I'll highlight some of the opportunities from quantum computing, which probably is pretty well known among this community, and move on to discuss business model innovation and economic productivity for the adoption of quantum computing. What's the impact on productivity and economic growth? And how does business model innovation play a role there? And what are the initiatives for productivity improvements and to drive economic growth going forward as we adopt quantum computing? So quantum computing promises productivity improvements and economic growth. As we know, what's the motivation for adopting quantum computing? It's driven by the miniaturization of semiconductors approaching the end of Moore's law due to quantum effects, and as well as exponential increase in computation time, which is rather well known, and due to the growth of data and so on and so forth. In fact, there's a wonderful report, an ATAC report, demystifying the capabilities of quantum technologies available today and in the future that highlights some of these improvements and efficiency improvements, as well as opportunities for economic growth. So, for example, it's possible that quantum computing will efficiently simulate quantum systems for new drug discovery, perhaps for new material discoveries, such as for clean energy. There's also opportunities for breakthrough capabilities in optimization, for example, in the financial services industry, looking at things like the valuation of financial portfolio, as well as fraud detection, logistics firms looking at the ability to better manage delivery of routing, and for manufacturing operations, so to speak, to optimize processes within the manufacturing environment. And also there are potential opportunities perhaps for enhanced speed of AI and machine learning algorithms as well. So these are some of the promises of quantum computing, which hopefully will contribute to productivity improvements and economic growth. However, if we go back in time and have a look at what happened with digital computing, the story is somewhat mixed in the beginning, so to speak. So here's a quote. And this is a quote by Robert Solow, who was a professor at MIT and won the Nobel Prize in economics back in 1987. And this is when digital computers was becoming prevalent among the corporate and firms, community organizations adopting them. And he made this remark to say, you can see the computer age everywhere, but in the productivity statistics. And this is quite well known as the Solow paradox and the productivity paradox by economists. And what did he actually mean by that? And in order to better understand what Robert Solow meant by this particular quote, we probably have to look at some of the statistics. So if we go back in time and have a look at productivity growth rates in the US. So US productivity, labor productivity displayed a J-curve effect following the adoption of digital computers. So if we look at the period 61 to 75, the growth rate was roughly about just above 2%. And then it slowed down between 76 and 1990. So in fact, the slowdown was about 0.76% before it took off again in the 1990s. So as digital computers were being adopted by firms, it turns out that it actually slows down productivity growth, and that actually resulted in a loss of output of about 23 billion in terms of GDP. And productivity here can be measured in different ways, but essentially the way to think about it is the amount of output of the economy relative to the input. The input could be labor, capital, and so on and so forth. In this case, it's labor productivity, but whichever way we measure it, we seem to see this slowdown in productivity before it takes off. Now, why does that happen? Because there is a huge learning curve in order to adopt a new technology, a general purpose technology such as digital computers. And that learning curve involves the adaptation of core processes and innovations to business models. Only when those core process and business model innovation are embedded within organizations and supply chains and industrial architecture do we really see an uptake in productivity. So an example here is if we go back and have a look at what happened in the retail sector. Walmart was adopting some of these digital computing technology back in the 1980s in order to try to share data among its suppliers. Now, it took them about a decade in order to re-engineer some of the processes, to reconfigure their business models so that the suppliers could share data across the entire supply chain of Walmart in order to ensure there isn't over and under production and the products are delivered at the right stores at the right time, and that enable economies of scale to be harnessed by Walmart and the retail sector that then enabled an improvement in productivity over time. Again, if we look at the manufacturing sector, a similar thing happened where manufacturers initially adopted some of these digital computers in order to transform a rather manual process into in digital format. Nothing really changed, and therefore productivity didn't really take off. Only when computer-aided design came along that enabled some of these manufacturers to come up with new products, to design them, to customize them for their potential customers going forward, did it enable new products to come on board and therefore data to be shared across the supply chain, and then productivity growth really took off, so to speak. So therefore, here again is an example where some of these technologies required time to be adopted and changed to influence the change of business models and core processes. Now, we think that quantum computing could be an even bigger drag on productivity growth. And there are several reasons for this. One is firms initially tend to look at quantum computers in an incremental manner. They look at a current problem that they're facing and seeing if it can't be computed fast enough by a digital computer, can I compute it using quantum computing? So the benefits are initially incremental, whereas the cost, because compared to digital computers that replace electromechanical computing machines, quantum computers are unlikely to replace digital computers. They are likely to be complementary and work together. And there's an integration cost, i.e. in terms of translating some of the algorithms and so on and so forth. So if you look at the ratio of the costs relative to the benefits, it's likely that the initial period there might be a drag on productivity. Number two is there's a cognitive drag. When we look at digital computers, it was relatively simple because digital computers works on a simple basis of switching electricity on and off in order to digitize a process, so to speak. And engineers and business managers would keep the technology under the hood at an arm's length to really adopt it. Whereas quantum computing is more difficult because the translation costs between the scientists, the engineers, and the business managers could be much higher due to the, I suppose, the slightly less intuitive nature of quantum mechanics that underlies quantum computing. Thirdly, there's a cryptographic cost, i.e. when we look at digital computers, there wasn't an equivalent cryptographic cost, whereas quantum computing is likely to potentially break some of the existing cryptographic encryption methods, and therefore firms are likely to invest first to defend themselves against that risk before they think about more innovative or new solutions for their customers, so to speak. So therefore, because of these three reasons, it's possible that quantum computing might be a bigger drag on productivity growth rates as they come on board compared to digital computers. So therefore, what can we do about it? This is a big question that I think managers and economists and policymakers need to get their mind around. First of all, I think we need a mission-driven approach in order to demonstrate the proof of concept in quantum computing. So as we've been speaking to a lot of stakeholders in this field, so to speak, users as well as potential users. These are suppliers, firms that are supplying quantum computing, or even enabling technology suppliers to the firms that are building some of these quantum computers. And we realize there is significant amount of uncertainty in the marketplace, i.e., most of the time, the users or most of these firms that are trying to use the technology, the experimentation is taking place more at a CTO level, or the technology level of the firm, and not so much. It hasn't really come up to a board level initiative, so to speak. Partly because there's a lot of uncertainty, and firms are looking and waiting for the technology to become more mature. From a supplier's perspective, again, there are challenges because certain firms that are supplying, let's say, a photonic component or a semiconductor component may not necessarily be willing to supply it to the quantum computing community because there are more lucrative markets elsewhere, so to speak. So in order to, and therefore this can be seen to some extent as a market failure, or there needs to be a market creation, let's say, and that requires a proof of concept via a mission-driven initiative, perhaps funding from the government, in order to align incentive between the enabling technology providers, the quantum computing firms, and the users, and even systems integrators that try to integrate some of the systems from both a technology perspective and a business perspective. So in order to align such incentives, perhaps a mission-driven approach whereby the idea would be to solve an industry-wide or a societal problem, so to speak. So, for example, if we take weather forecasting or financial market stability, these are areas where individual firms may not necessarily be willing to invest on a private basis. However, these are initiatives whereby there are tremendous opportunities for a public good, so to speak. So therefore, a mission-driven approach funded by the government in order to align the incentives in order to tackle, let's say, a weather forecasting type problem or financial market stability type issue, where each individual firm may not be willing to invest in it, but it's nevertheless useful for them collectively, would enable the proof of concept of a quantum computing proposition. And once the proof of concept is demonstrated, then there could be more private sector investments coming in, and therefore potential uptake in the technology in order to drive productivity and economic growth. The second issue, as I mentioned, is this cognitive drag. Quite often, there is a lack of shared language between scientists, engineers, and business managers. And we've heard this many times through our interviews, whereby the language that's used by scientists and the language that's used by engineers and the business language that managers require are quite different, especially from an understanding of quantum computing. And therefore, this lack of shared language can be a problem in order to, first of all, identify the right class of problems that a quantum computing might be helpful from a business perspective. In addition, what kind of information that would be helpful for the community or potential users to think about. It requires a good understanding of the underlying technology and the business problem, and because the language that is being used in this different technical development as well as business application is quite different, it could be quite challenging. And thirdly, how does one prepare the right type of data in quantum-ready format that can be used to do some of this computation, and requires a good understanding of how those technologies need to be translated between, let's say, a digital computer and a quantum computer, and vice versa, so to speak. So, for example, if we take the example of a logistics firm, so a logistics firm may currently plan their logistics routing perhaps every overnight, because the digital computers are such that it can only plan it takes time to plan the routing. But in a world where we are buying more and more things online, customers are also returning a lot of things on quite often, having bought them via an e-commerce or online channel. So therefore, for a logistics firm, it's imperative that they're able to perhaps recalculate their customer routing algorithms and plans as and when such customer returns are taking place. However, this may have a knock-on effect, i.e., it has a knock-on effect on the inventorying system within the firm or the financing system within the firm. So therefore, some of these core processes and business models need to be realigned, and understanding that wider implications for management, i.e., for business managers to say, okay, if I do adopt a quantum computer, there could be all of these knock-on effects on some of my other core processes, is an important part of understanding the opportunities for performance improvement and economic growth for the firm. So therefore, having a common language between the scientists, engineers, and business managers is important. So having a common semantic or synthetic language for quantum computing, i.e., can we actually develop some kind of a unified modeling language that is visual, that would be simple for managers to understand some of these modular workflows, to understand the prototyping and test bedding and roadmaps in how some of these core processes and business models and even across the industry architecture or supply chain needs to be made simpler in order to overcome some of this cognitive drag that may take place as a result of quantum computing coming on board. We already begin to see some of this, say, for example, in computational chemistry, some of these quantum computing firms are beginning to develop such modular workflows. This needs to be enhanced and brought wider into other sectors to really get quantum computing to be adopted more widely. Now, the final element is I mentioned this idea of the cryptographic risk, so to speak. So if we go back and look at digital computers really took off when the internet came on board, because they were able to connect a lot of computers globally, and therefore new business models and new value propositions and platform-based business models and so on and so forth were developed on the back of internet-based connectivity, so to speak. And there's an opportunity here, instead of getting firms to think very defensively about the nature of quantum computing to defend themselves against cryptographic risk, if we were to be able to accelerate the building of a quantum internet with secure encryption, the idea being to combine quantum computing with networking technologies so that there is an opportunity to perhaps adopt more distributed computing technology on the back of this quantum-based internet. And this will perhaps overcome some of the security threat and spur growth. So one example of such a initiative is, if we look at that can enable new business model, is the idea of blind computation. So in principle, the integration of quantum computing with some of the encryption using quantum mechanical principles could, in principle, provide blind computation, i.e., some of these quantum computers could do a computation where the computers doesn't really know precisely what the computation is, so to speak. Now, this could be very beneficial, particularly in a world where we want to share, let's say, production facilities. So, for example, factory systems shared across firms enables the private computation while preserving private data, so to speak. So the idea being, if different firms are able to share their production capability, for example, using 3D printing facilities and so on and so forth, there's an opportunity here to actually share the learnings from how the 3D printing machines are working across one factory to another, without necessarily revealing anything that would compromise the specific production techniques of one firm compared to another. So this could result in, say, better optimization of the network of factories with sharing capacity across them. And this could actually result in, for example, localized production, which may help things like the sustainability or net zero initiatives and so on and so forth. So the idea here is to get firms to think about very quickly moving away from a defensive mode to think about what are the new value propositions that could arise, just like what happened with digital computers and the internet, so that the benefits come through more quickly, and therefore the drag on productivity, as I mentioned earlier, may be curtailed, maybe not completely removed, but at least curtailed, so to speak. So in summary, The general purpose technologies usually cause slowdown in productivity growth before takeoff. This has happened in various general purpose technologies. So we go back in time and have a look at digital computers or the replacement of electric motors with um, 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 steam engines and so on and so forth. We see this pattern, so to speak, where the learning and adaptation costs to change core processes and business models takes time, and that could slow down productivity before it takes off. Quantum computing is likely to contribute to such slowdown in productivity growth because of this incremental benefits initially relative to the cost of integration, the cognitive drag, the complexity of explaining what a quantum computing is, and their cryptographic costs, so to speak. So therefore, we need to be able to enable faster learning and business model innovation to address some of these grand societal challenges and contribute to productivity and economic growth, so to speak. So it's important, just to go back and really understand how some of these general purpose technologies have been slowing down productivity growth before takeoff, why quantum computing could contribute to such a slowdown, and we need to enable faster learning and business model innovation to address these grand societal challenges and to enhance or at least to retard such a slowdown in productivities so that it benefits society and contributes to economic growth quicker. These are just some references that anybody who wants to follow up and based on some of the work that I've been doing, happy to answer any questions. Thank you very much.
Thank you. If there's any questions from our audience, please go ahead and click on the Q&A button and type it in, and we'd be happy to address it.
Okay, I have a question here. Where do you foresee the workforce coming from? What sectors to contribute to these solutions?
Right. So yes, the workforce element is quite an important part of this solution, and I think workforce has two parts to it. One is what I'm calling the technical capability. In terms of understanding some of these technologies and so on and so forth. And quite often the technical capability could be, the universities are beginning to develop courses around quantum technologies and so on and so forth. However, I think some of the initial technical capability might come from people who are trained in adjacent, let's say, subject areas, i.e. in electronic engineering or computer science and so on and so forth. So one is the technical capability, but in addition to that, based on our work, it is important in order to train and develop what I'm calling quantum leadership among the senior management, because even if we were to develop the technical capability, there is a big challenge in how do we get senior management to really understand the benefits of this technology, willing to take the risk and investments that is needed in order to adopt them and enable the transformation of businesses, so to speak. And that is a second type of a capability, and that's a capability that we have been recommending, particularly in the UK, to the national program and so on and so forth, to emphasize the importance of that kind of skill set building in addition to the technical development, so to speak. And I hope, we hope very much the skills around the leadership of quantum technologies is jointly developed in complement with some of the technical development. So that will be a way forward.
Thank you. The next question is, do you have specific examples of actions or programs that governments can use to minimize the adoption cost by the private sectors?
Yeah, it's interesting. I'm familiar with the UK program, and I've been looking at some of the programs in the US as well as across Europe. The UK program is quite unique because the program started almost 10 years ago. So I think the UK was the first country to have a national program. And the UK program has had over the last 10 years a number of initiatives, so to speak, i.e. they've funded quantum technology hubs, so to speak, including quantum computing, and also funded joint initiatives between firms that are potential users, i.e. these are the Rolls Royces of this world and so on and so forth, and or BAE Systems and so on, and firms like that, together with some of the firms that are developing both the technical capability, the technology capability, as well as some of the software capabilities. So for example, in the UK, you've got firms like Riverlane looking at things like error correction. So how do you bring all of these different parties together in order to explore, understand, and develop the technology? So that's a great example. And in the UK, we've also had more recently a testbed initiative. So the UK has, and it's very unique in the UK again, has got a national program, a national lab called the National Quantum Computing Lab. They've funded 7 test beds. 3 of them are American firms and 4 of them are UK firms. And the idea here is, how do I build out the technical capabilities by bringing in an ecosystem of business users in order to, I suppose, to improve the learning between the technical development and the business use cases, therefore to reduce the time scale that is needed to adopt some of these core processes and enable business model innovation.
Thank you. The next question is, how long do you think it will take China to chain together D-Wave machines to crack the 256-bit encryption?
Oh, goodness. Okay. That's a difficult question. I don't think I am in a position to be able to answer that, because it's quite difficult to get a full understanding of what the Chinese initiatives are. So I'll take a pause on that specific question, because I don't think I'll be able to give a reasonable answer to it, so to speak.
Thank you. All right, the last question I have in the Q&A is, what is the biggest hindrance in commercialization of quantum tech?
Yeah, I think, quite often with these kinds of new technologies, one of the biggest challenge often is what I'm calling the cognitive mindset, i.e. how do you get senior management to change their mindset about what a new technology is? And that's quite a challenge, because first of all, initially, it's not clear what the technology is. Number 2 is organizations quite often have been successful on a previous generation technology. And that could happen here as well, i.e. the very fact that some of these large corporations have been successful because they've adopted digital computers or digital based related technologies. There's a risk that they frame a new technology like quantum technology or quantum computing and so on and so forth in the same light as a previous generation technology, and that can often be a major challenge. And therefore, trying to educate and change mindsets, I think, will be the biggest hindrance for the commercialization of quantum tech in general, and maybe even quantum computing in particular.
Yes. Thank you. We actually got another. It was like a 2-part question that was posted. Would you say that most companies are waiting for a quantum advantage before planning investments? That's the first part. And then the second part is, outside of government funding initiatives, are companies investing in quantum workforce training or building their IT departments with quantum engineers?
Yeah. I think that's absolutely right. I.e., some firms are waiting for this quantum advantage before investing. And I think that may be a strategic error, because there are quite a lot of things that can be done in order to do some quantum inspired type computing, in order to get the firms ready, so that as the technology becomes more mature, they're much more capable of adopting it, transforming processes and business models and so on and so forth. So the idea that we need to wait before we invest is could be a problem, but the natural tendency is for firms to do that. Now, outside government funding initiatives, yes, absolutely right. I mean, certain industries where they can see more immediate benefits. Financial services is a classic example because if we compare it to, say, pharmaceuticals and so on and so forth, the likely benefits is going to come many years down the line, perhaps in drug development and so on and so forth, because it takes quite long to develop a new drug, even with the simulation capability that of a quantum computer. But in the financial services sector, it's possible that some of the benefits may accrue quite quickly, and therefore we see the banks in particular investing much more systematically in trying to build teams, because they probably see a more immediate impact on the financial, on their P&L and their income, and therefore they're beginning to train their own workforce, so to speak. So maybe that would translate into some of the other industries as well.
All right. Thank you. I don't really see any other questions in the Q&A. And we're at time anyway. So Amy, you have any follow-ups or anything?
No final comments for me, but I wanted to say thank you everyone for attending today, and thank you, Chander, to your wonderful presentation.
Wonderful. Thank you. Thank you very much, Amy. And thank you, Jason. And thank you everyone for attending, and much appreciated.